All right, good morning, y'all. Today we're going to be talking about mole concept. Mole concept is something that's real important. Today is just going to be the beginning of that. Before we get into the mole, though, I want to talk about something called a quantitative word. So, quantitative word. So, a quantitative word is, well, before I tell you guys, let me see if any of my students know what it is. All right, so in front of you, you see some examples of quantitative words. These are words that the students came up with. So quantitative words are words that represent numbers, and they always represent the exact same number. Roses and eggs are conveniently packaged in dozens. We know dozens are 12. So sheets of paper are always packaged in reams. A ream is always going to be 500 sheets. And the same is true for atoms. So because atoms are really small, the amounts of them that are packaged together are really, really big. A package of atoms or compounds that chemists use is called the mole. So you're going to write this on your page. So a mole, and here's just some more information on the mole. So a mole is constantly, I'm going to be abbreviating it to MOL. So anytime you see MOL, know that we're talking about a mole. All right, so a mole is constantly going to be abbreviated MOL, just so y'all know what that is. I do that all the time. And it contains 6.022. You can see this number. It's a really, really large number. And the decimal doesn't show up until right here at the end. So this number is ginormous. Let's count up these zeros. So here we got 3, 6, 9, 12, 15, 18, 19, 20 zeros that come after the 6.022. So it's an enormous number. This is called Avogadro's number. You want to write that down? I constantly refer to it as Avogadro's number. You need to know what I'm talking about. So what I would write for mole, if I were you, is mole is MOL, and MOL is also called Avogadro's number. And a mole is 6.02 times 10 to the power of 23. This last two, we don't really need to count it, so y'all don't need to worry about it. So 6.02 times 10 to the 23rd. So you're going to memorize this number very, very soon. We're going to be working with it so much that you're going to know this number. But it's also provided to you on the periodic table that you're going to get on the ACP. But you are going to memorize it, so don't even worry about it. So this is basically what you need to know about a mole. Next, we have a few words. So we got representative particle. And a representative particle is just a thing. And 4 things fall under this category. So atoms fall under this category, molecules, compounds, and formula units. So can anyone give me an example of an atom? I'm going to pause so that y'all can talk to me. Examples of molecules are going to be things like O2. So O2 is going to be an oxygen bonded to another oxygen. It doesn't qualify as a compound. That's a molecule. A compound is going to be something that's chemically bonded to another type of atom. An example of that is going to be CO2. And then all of these are considered formula units. So a formula unit is just a formula of anything. So that's a formula unit. So all of these things are considered particles. Moles, they tell you particles, and like atoms, molecules, compounds, and formula units all qualify and fall under particles. All right, so the mole is not only handy in counting large amounts of atoms. It is even more useful when measuring amounts of elements and compounds. The masses on the periodic table have been designed to be the amount of grams in 1 mole of that element, thus called the molar mass. So the molar mass is going to be the mass of 1 mole of any element on the periodic table. This is the last piece of new information you're going to get on the periodic table. We've been calling this the mass number. Moving forward, I'm going to be calling it the molar mass. So 1 mole of sulfur has a mass of 32 grams. And also, we're going to be rounding these to the nearest whole number. There's a couple that are really annoying to round to the nearest whole number, like chlorine, which is going to be 35.5. I'm going to let you guys keep chlorine at 35.5. Everything else, I want it rounded to the nearest whole number. So 1 mole of anything is the mass number, or the molar mass that's given to you on the periodic table. So 1 mole of fluorine is equal to 19 grams. 1 mole of neon is equal to 20 grams. Like back to what we were saying on the previous page, 1 mole of anything is equal to 6.02 times 10 to the 23rd particles. Particles or atoms or molecules or compounds. So the information shown for sulfur tells us that 1 mole of sulfur is equal to 32 grams. Likewise, 2 moles of sulfur are going to be 2 times 32, or 64 grams of sulfur. So let's say I said that we have, if we have 1 dozen donuts, we have 12 donuts. If we have 2 dozen donuts, that means we have 2 times 12, which is equal to 24 donuts. If we got 3 dozens, it's going to be 3 times 12, which equals 36 donuts. And that's how we're going to be calculating molar mass moving forward. So this allows for amounts of elements to be easily measured out in a laboratory and churned into moles. So what you guys are going to be doing is calculating molar mass. A compound is a collection of atoms that are bound together. We know what a compound is. So here we have 1 mole of methane. What does that mean? It means we have, so 1 mole of methane is equal to 6.02 times 10 to the 23rd particles of methane. So how many carbon atoms do we have in 1 mole of methane? So because there's only 1 carbon in methane, it's going to be, we have, so 1 mole of methane of CH4 is equal to 1 mole of carbon, which means that we have 6.02 times 10 to the 23rd carbons. But in a CH4, we have 4 hydrogens. So think about this like if we have a dozen motorcycles. So 1 dozen motorcycles. If we have a dozen motorcycles, how many motorcycle wheels do we have? So if we have a dozen motorcycles, that means we have 12 motorcycles, but we're going to have 24 wheels because each motorcycle has 2 wheels. And if we were talking about a dozen cars, that means we have 12 cars. But if we were talking about how many wheels we have, excluding the spares, it's going to be 4 times 12, which gives us, I don't know, what's 4 times 12? 48? But that's the math that we're doing right here. So coming back to this, in 1 mole of CH4, we have 4 moles of hydrogen. And we know that 1 mole of hydrogen is equal to 1 gram. So if we have 4 moles of hydrogen, how many grams is that? It's going to be 4 grams. So let me go ahead and clear this, and I'm going to show you how to calculate the molar mass. So first thing we're going to do for all molar mass calculations is we're going to write out the element that we're calculating the mass for. So for this one, we got CH4. Then we're going to write out all the compounds, all the elements in the compound. So we're going to have carbon, and we're going to have hydrogen. Then we're going to write out how many of each one we have. So we have 1 carbon, and we have 4 hydrogens. Then we're going to write the molar mass, and we get that straight from the periodic table. So carbon has a molar mass of 12, and hydrogen has a molar mass of 1. Next thing we're going to do, we're going to add them, or we're going to multiply straight across. So 1 times 12 gives us 12. 4 times 1 gives us 4. And then last step is we just add these together, and that gives us 16 grams per mole. That's calculating the molar mass of CH4. I'm going to do one more example just like this one. So let's do H2O. So we write out the compound, and then we write all the elements in the compound. So we have hydrogen and we have oxygen. How many hydrogens do we have? We have 2. How many oxygens? We have 1. And then we put in their molar masses. So hydrogen always has a molar mass of 1. Oxygen has a molar mass of 16. We multiply straight across. 2 times 1 is 2. 16 times 1 is 16. We add them together. That gives us 18 grams per mole. So 1 mole of H2O is equal to 18 grams. That's calculating molar mass. I don't want to spend too much time on this, but I'm going to give you all a few minutes to practice. We have some practice problems on not this slide, but the following slide. So for compounds containing ions, the molar mass is obtained by summing the masses of the compounds. This is sometimes called the formula weight. So this is no different than what we did before. So NaCl, we have Na and we have Cl. Sodium has a molar mass of 23. So Na times 1 times 23. And then Cl is going to be, so chlorine is that annoying one that I told you is going to be 35.5. But that's going to be 1 times 35.5. And then we just add them together. And then that's going to give us 58.5 grams per mole. So 1 mole of NaCl has a mass of 58.5 grams. Here are some practice problems. I'm going to give you all a few minutes to work on. I'm going to do one of these for you, and then I'm going to let you guys work out the rest. So let's do that first one. So we got sodium nitride. So first thing we're going to do on our page is we're going to write out the formula. We got Na3N. Then we write out all the elements in the compound. So this has sodium and this has nitrogen. Then we write in how many of each we have. So sodium, we got 3 of them. Nitrogen, we have 1 of them. Next, we bring in the molar masses. So sodium has a molar mass of 23. Nitrogen has a molar mass of 14. We multiply straight across. So 3 times 23 gives us 69. 1 times 14 is 14. Then we just add these together. So that gives us 83 grams per mole. So 1 mole of Na3N has a mass of 83 grams. All right, so I'm going to give you guys 1 minute. I want you to solve the next one. Shouldn't take much longer than that. So go ahead, get started. All right, so I'm going to do one more example, and then we're moving forward. Last one I'm going to do is H2SO3. So we write out all the elements in the compound. We have hydrogen, sulfur, and oxygen times 2 times 1 times 3. Then we put in the molar mass. That's 1. Sulfur is 32. And then oxygen is 16. So 16 times 3, I'm going to use my calculator. That's 48. 32 and 2. We add these together, and that gives us 82. Did we all get 82? All right. So that's going to be it. This thing is not hard. If you have any issues with this, they're pretty easy to learn, so we can just take care of it in tutoring. Let's go ahead and move on to what we really have to do today. So a student measures out 12 grams of magnesium in a lab. How many moles does this student have? So I'm going to put some conversions on the board. So we know that 1 mole is equal to 6.02 times 10 to the 23rd particles. So here we're talking about magnesium, so I'm going to put atoms. We also know that 1 mole of magnesium has a mass of 24 grams. So 1 mole of Mg has a mass of 24 grams. So if a student measures out 12 grams, are we able to figure out how many moles they have? Yes or no? Yes, we are. So the way that we're going to do this is using dimensional analysis. And what that is you put a line down the paper, and I'm going to be calling this the train track. Later on, it's going to look like a train track. It just goes on and on. So we're going to be calling this the train track. I want you guys to write this exactly how you see it, because this is the work that I expect to see on assignments and tests. So this first box up here is going to be your given information. Your given information is whatever you're given in the question. So here we're given 12 grams of magnesium. That's what goes in this box. 12 grams of magnesium. This box down here, you could put a 1 here, but a 1's not going to affect the problem. What I would do if I were you is completely ignore it or exit. Doesn't really matter. This box is always supposed to stay empty. It says how many moles does the student have, and we have grams up here. Whatever unit you have in this box needs to be the same unit that you have in this box. The conversion that I wrote down here earlier was 1 mole of Mg is equal to 24 grams of Mg. This is the conversion that we're going to plug into our train track. So because we have grams up here, we're going to need to put grams down here. So 24 grams of magnesium. And that's equal to 1 mole of magnesium. Now, the way dimensional analysis works is we always divide by the bottom, and then we multiply by the top. So everybody grab your calculator. We're going to do 12 divided by 24. That's going to give you 0.5. And then we take 0.5 and we multiply it by 1 mole of magnesium. What's our final answer going to be? It's going to be 0.5 moles of magnesium. So when we divide by 24 grams of magnesium, we're canceling out the grams and the magnesium. This goes away. And then 12 divided by 24, that gives us our new number, which is 0.5. And then when we multiply by 1 mole of magnesium, we pick up our new unit from right here. So this is your answer to this question. Once you have an answer, I want you to put it in a box. It makes grading a lot easier for me. So this is how you solve this type of problem. All right, so the opposite could also be done. So we're given moles in this one, and they're asking for grams. So this is going to be solved more or less the same way. First thing we're going to do, we're going to create our train track. And then this box, that box gets our given information. So we're going to put in 2.3, and you can put the 0, it's up to you, 2.3 moles of boron. So we know that 1 mole of boron is equal to 11 grams of boron. So because we have moles up here, we need to put moles down here. So 1 mole of boron is equal to 11 grams of boron. We're always going to divide by what's at the bottom, and then we multiply by what's at the top. When we divide by the bottom, we're going to lose our unit, moles of boron. That goes away. And the 1 doesn't affect our number. So we're just going to multiply. It's going to be 2.3 times 11 grams of boron. So everybody plug that into your calculator. You should have got 25.3 grams of boron. So 2.3 moles of boron is equal to 25.3 grams of boron. All right, so if you know the number of moles, then the amount of atoms can also be calculated. So we know that 1 mole is equal to 6.02 times 10 to the power of 23. So how many atoms are in 2 moles of aluminum? So if I were to say how many atoms are in, well, no, I'm no need for it. So how many atoms are in 2 moles of aluminum? We know that 1 mole is going to be 6.02 times 10 to the 23rd. So we're just going to use our dimensional analysis here. Our given information goes in that first box, and we have 2 moles of aluminum. So because we have moles in this box, we need to put moles in this bottom box. So we're going to put 1 mole of aluminum here. And we know that 1 mole of aluminum is equal to 6.02 times 10 to the 23rd. And that's going to be atoms of aluminum. So the big mistakes that happen in this type of math is being input in the calculator incorrectly. If you don't put this in the calculator right, you could have tried to do the right thing, but the calculator will give you the wrong answer. So it's very important to put this in the calculator correctly. Before we plug it into the calculator, though, let's see what happens here when we divide. So when we divide by the bottom, the moles of aluminum goes away, and the 1 doesn't change our number at all. So all we're doing here is 2 times 6.02 times 10 to the 23rd. And the way you're going to plug that into your calculator is 2 times, open parentheses, 6.02 times 10, and then you're going to find the caret button. If you're using a TI-83 calculator, the caret is right under the clear. So hit the caret button, and then to the power of 23, and then you're going to press the forward arrow, and then you're going to close parentheses. If you don't press the forward arrow before closing the parentheses, it's going to give you a syntax error. So make sure that you plug it in just like this. And I'm going to give you all 15 seconds to give me an answer. All right, so this next one says, how many moles are in 9.3 times 10 to the 23 atoms of potassium? So again, we're going to do dimensional analysis. Given information goes in the first box. That's going to be 9.03 times 10 to the power of 23. And this is atoms of potassium. So our conversion is going to be 1 mole is equal to 6.02 times 10 to the power of 23. So because we have atoms up here, we need to put atoms down here. So we're going to put 6.02 times 10 to the power of 23 atoms of potassium is equal to 1 mole of potassium. Then we're just going to divide by the bottom, and then we're going to multiply by the top. So this one is no different than the previous one, except here we're dividing by 2 numbers with in scientific notation. So this is just a little bit more difficult to input in your calculator. The way this needs to go in is open parentheses, 9.03 times 10, caret 23, forward arrow, close parentheses, division sign, open parentheses, 6.02 times 10, caret 23, forward arrow, close parentheses. So go ahead, try to input that. I'm going to give you all 30 seconds to get the answer. All right, so our previous work with representative particles and molar masses can also be combined. So this is going to be the most difficult type of problem you're going to see on this ACP. The next ACP for next semester is going to be just a few more steps than this. But everything we've worked so far has been a 1-step conversion. What we're about to do are going to be 2-step conversions. So in a 2-step conversion, you're going to do the same train track, except this time we got 2 dividers. So a student needs 2.6 times 10 to the 23 atoms of fluorine for an experiment. How many grams of fluorine should the student measure out? So our given information still goes in this box, and that's going to be 2.6 times 10 to the power of 23, and that's going to be atoms of fluorine. And y'all are probably thinking this is redundant. Why do I put atoms of fluorine? Because you need to know that whatever unit is in this box needs to be the same unit that's in this box. So if we have atoms of fluorine up here, we need to put atoms of fluorine down here. So our conversions, the ones that we're going to use for this one, is 1 mole is equal to 6.02 times 10 to the 23rd. And then the other one is going to be 1 mole of fluorine is equal to 19 grams. So our first box is going to be this one right here. We're going to put 6.02 times 10 to the 23rd atoms of fluorine, and that's equal to 1 mole of fluorine. Our next conversion is going to be to convert from moles to grams. So because we have moles in this box, we need to put moles in this box. So 1 mole of fluorine is equal to 19 grams of fluorine. So we're going to solve this just like we did the previous one, except this time we just have an extra step. So I'm going to clear this space so that I can show y'all what needs to go in the calculator. So first thing we're going to do is we're going to divide by the bottom. We're going to multiply by the top. When we divide by the bottom, we're going to lose our unit, and our number is also going to change. When we multiply by the top, we're going to pick up this unit. And then we're going to divide by the bottom again. So this unit goes away, this unit goes away. And these ones, you know that they're not going to do anything. Multiplying by 1, dividing by 1 isn't going to change anything. So we're going to take this number, divide it by Avogadro's number, and then we're going to multiply by the molar mass of fluorine. So the way this goes in the calculator is open parentheses, 2.6 times 10 to the 23rd, so caret 23, forward arrow, close parentheses, division sign, open parentheses, 6.02 times 10, caret 23, forward arrow, close parentheses, and then times 19. You don't have to do this in one step. You can do it in one step, but if you'd like, you can divide it into 2 steps. So first thing you do is plug this into the calculator, and then whatever answer you get, you just multiply it by 19. So it's up to you. I'm gonna give you guys, I'm gonna give y'all 1 minute to do this one. Make sure that you get the correct answer. All right, so what's the answer we got for this one? All right, so 3 significant figures is enough for me. So 8.2 what? Okay, so this just becomes 8.21. And what's our unit? What's the unit? Grams of what? Grams of fluorine. So did we all get the same answer here? All right, good. Let's go ahead and move on. All right, so this one I want y'all to try doing on your own. All right, let's go ahead and solve this one real quick. So our given information is going to be 56.7 grams of aluminum. We know that we need to put grams down here. The molar mass of aluminum is going to be 27 grams. So 27 grams of aluminum. That's going to be for 1 mole of aluminum. And then our next conversion is going to be moles to particles. Because we have moles up here, we need to put moles down here. So 1 mole of aluminum is going to be equal to 6.02 times 10 to the 23rd aluminum. So our first step is going to be to divide by the bottom, multiply by the top. All we're going to do here is we're going to pick up this unit, which we're going to get rid of in a minute. And that's going to be atoms of aluminum. So the equation that you're going to plug into your calculator should look like this. Open parentheses, 56.7, division sign, 27 grams, or not grams, just 27, close parentheses, and then we're going to multiply, open parentheses, 6.02 times 10, caret 23, forward arrow, close parentheses. So if you haven't plugged it into the calculator yet, let's do it right now. Let's see if we can get the same answer. All right, sorry, you're going to have to repeat that a little bit louder.
1.2642
times 10 to the power of 24. And what's our unit? It's going to be atoms of aluminum. We get that from right here. So this last box always gives us our unit. All right. So that's enough of the PowerPoint. Now we're going to work on today's assignment. So let's pull that up real quick. So usually I'll show this to my students in the beginning. It's very, they usually find it pretty helpful. With you guys, I wanted to show it to y'all at the end. I want to show y'all how to solve the problems, and this right here is just a cheat sheet on how to get your answers. So over here, it shows you how these conversions need to go. Can we go from, one second, let me change my tablet settings. So can we go from mass to particle in one step? Yes or no? What do we have to do first? We have to go from mass to mole, and then we can go from mole to particle. So this triangle, it shows you guys volume as well. We're not going to be working with volume until next semester, so you can ignore this part right here. But if you want to write this down in your notes, this section, it shows you exactly what you're going to do when you're going from one part to another. All you do is follow the arrows. So let's take a look at number 1A. This worksheet's what you guys are going to be working on today. The expectation is you finish 1 through 4. Next time we'll work on this next part, but 1 through 4 is what I need from you guys today. So let's take a look at number 1. Number 1 says identify and calculate the number of representative particles. So they want to know the number of atoms in each of the following. So they start us off at mole, and they want us to go to particles. So if we're going from mole to particle, what's our what's the equation that we use? We're just gonna follow the arrows. So over here, I'm gonna set it up over here actually. So our given information is gonna be 2.15 moles of gold, so moles of AU, and to go from mole to particle, we're just gonna multiply by Avogadro's number. So 1 mole goes at the bottom, and then 6.02 times 10 to the 23rd goes at the top. And that's it. This is a one step. So we divide by moles of moles of gold, and that goes away. The 1 doesn't affect anything, so the number stays the same. And then when we plug it into our calculator, it's going to be 2.15 times, open parentheses, 6.02 times 10, caret 23, forward arrow, close parentheses. So I'm going to give you all 20 seconds. I want y'all to give me an answer to this one. So first thing we're going to do, we're going to put in our given information. That's going to be 3.05 moles of lithium. And then because we have moles up here, we need to put moles down here. And we're going from moles to mass. So let's come back and take a look here. So if we're going from mole to mass, we're going from here to here. What are we doing? We're dividing by the bottom. Does dividing by 1 do anything? No, it doesn't. So what are we actually doing to go from mole to mass? We what? So if the number's at the top, what do we do? We multiply by the molar mass. So to go from mole to mass, we just multiply by the molar mass. So 1 mole goes down here, 1 mole of lithium. And then the molar mass of lithium is going to be 7 grams. So 7 grams of lithium. This one should be fairly simple. You divide by the bottom. That gets rid of our units. And then you multiply by the top. And then that's going to give you your answer. I'm going to stop right there. You should be able to do the rest of that one. Let's go to number 3. How many particles are in the following sample? So 3 and 4 are going to both be 2-step equations. So for 2-step equations, you're going to need 2 dividers. So we're going to start by putting in 1.24 grams of cesium. And then because we have grams up here, we need to put grams down here. The molar mass of cesium is going to be 133 grams of cesium for 1 mole of cesium. And then our last step is going to be to convert to a number of particles. So we have moles up here, so we need to put moles down here. So 1 mole of cesium is equal to 6.02 times 10 to the power of 23 atoms of cesium. And then we just divide by the bottom, multiply by the top, divide by the bottom, multiply by the top. I'm not going to plug this one in for you. You can just go ahead and plug that one in yourself. But I want to show y'all something. So in this one, we're going from mass to particles. So we're starting here and we're ending up here. So to do that, all I did was plug this equation and then I plugged this equation. So the key that you have at the top is extremely valuable. I would use it, but also just have an understanding of why we put this at the bottom. We put this at the bottom to get rid of this unit. We want grams of cesium to go away because we're trying to convert to moles. Then we want moles of cesium to go away because we want to convert to atoms. And that's going to be it. I'm going to do one more, number 4a, and then I'm going to let you guys work on your own. So first we put in our given information, so 4.16 times 10 to the 23 atoms of radium. And then because we have atoms up here, we need to put atoms down here. So that's going to be 6.02 times 10 to the 23rd atoms. That's going to be for 1 mole of radium. And then we have moles up here, which means we need moles down here. 1 mole of radium is equal to how many grams? So radium is 226 grams. So then we just divide by the bottom, multiply by the top, divide by the bottom, multiply by the top. And that's going to be it for today. You have the rest of the class to work on 1 through 4. The goal is to finish 1 through 4. We'll see how far we get, and that's going to be it.